All right. So yeah, welcome everybody to the second lecture of CS 6530 Advanced Databases. I'm Yuvraj. I'm the class TA. The professor is traveling. He should be back for the next class. So I'll be taking this class. Uh, so today I'll be giving you sort of a crash course to multi-threaded programming. Um, some of this might be very familiar to you if you've already done this kind of thing. Hopefully, there's some stuff, there's some new stuff that you get from this. I'll do a demo of how to profile code in Linux. So hopefully that part is a bit new. For everyone else who is looking at this sort of thing for the first time, it might be a bit confusing. At least it was for me when I saw this stuff for the first time. So feel free to stop me at any time. We might have to stare at a few code sections for a bit longer, but that's okay. So make sure you get everything from this lecture. The stuff that I'm going over here is heavily tied into the first project. We'll release the project, I think tomorrow or Monday. You don't have to start working on the project. I think we're planning for around like 2 or 3 weeks. So you have time. But the stuff we're covering here will be very useful for project one. So the first half of the lecture, I'll just go over some basic primitive synchronization concepts that you need to know to program any multi-threaded application. And then in the second half of the lecture, I'll log into the CADE machine, run a few examples, and show some of the project one stuff that you're expected to do. So feel free to stop me at any time, ask questions. Yeah, any questions? All good? Okay. I'm recording this lecture, so hopefully. So yeah, I think in the last lecture we covered about how data set sizes are like exploding rapidly. And you need high performance applications to process these large sets of data. And critical to getting high performance is being able to program in a multi-thread environment. So processor speeds are kind of stagnating. Single core processor speeds are not increasing. There are a bunch of reasons for that. Uh, uh, Moore's law is ending, and it's not it doesn't make financial sense to keep increasing those clock speeds. So these days it's more normal to have lots of cores with a whatever baseline single core speed that's reasonable for that, but divide the work across multiple cores. So this is a machine I work in the lab. It's a pretty beefy machine. It has 128 CPUs, each around 2 gigahertz. It's an Intel Xeon Gold. So what I've seen is processors have, like, at least the high-end cloud machines, bare metal, have around hundreds to maybe 200 cores. GPUs, it's even larger. You get into thousands and 10,000s. Again, nothing surprising here. So what I'm trying to tell is it's good to know how to program multi-thread applications. The problem is, as some of you who might have done multi-threaded programming, is it can be a bit unintuitive, especially if you're seeing it for the first time. There are a lot of programmer assumptions that at least I used to have before, like looking at multi-thread programming, that just break down, right? So we'll go over a few of those unintuitive behavior, how to fix those, and then that should get you started with writing these multi-threaded programs. So the first intuition is that when you write a single line of code, say like simplest example, x equal to x plus 1 or some multiplication, even though it's a single line of code in your program, that does not necessarily mean it's a single instruction on the CPU, if that makes sense, right? So when we write like a function or a single line of code, if you're not aware of this, like you might have the assumption that when I invoke a function, the entire function runs or none of it runs. You don't expect the function to be interrupted in between. This is true for a single threaded program, right? Like once at least, yeah, I mean, if you're writing single threaded code, once you're inside a function, nothing's going to interrupt the function. The entire function, it's sequential. It happens one after the other. So you have these notions of atomicity, like the entire function executes or none of it executes. That kind of breaks in multi-threaded when you start programming in multi-thread with more than one thread. So this is a simple example. Hopefully, it's has anyone never seen C code before? You've not seen C code, or right? I'll go over this code snippet. So the first block over there is a simple function that takes a pointer to an integer, and I'm passing it a parameter called times, and I'm looping over the number of times and incrementing the pointer by one. It's some work, right? And then there are two blocks. The first one calls this increment function 2 times with some I think that's how much is it, half a million, and prints it out. The second one tries to increment, do the same thing, but split the work across 2 threads, right? So don't worry about the thread API as long as you get that the second application is trying to do the first function in like concurrently, you should be good. Okay, so this is if what do you expect the output to be for the first one and for the second one? Anyone? It's not a trick question.
500,000.
No, I'm adding it twice. So
Oh, I see.
1 million, right? 1 million for the first one. What about the second one?
Same.
Right. If that's what you would expect if you had this notion of x equal to x plus 1 being atomic. But what actually happens is the first one executes as expected. The second one, you get different values each time you run it, right? So what's actually happening here? What's actually happening is x equal to x plus 1 does not really translate to one instruction. So this is not exact assembly code, but it's a good representative of how the x equal to x plus 1 is translated to assembly code. And these 3 instructions are basically what gets executed on the CPU. Right? So the first one is load x into the register 1. The second one increments like store the result of R1 plus 1 into R1. And the last one is store the value of R1 into X. So the thing about CPUs is any arithmetic operation or any comparison or whatever operation you need, it needs to load its operands into its registers locally. And then it does the arithmetic. So it can't directly read the value from memory. It needs to load the value from the memory into its register and then does this whatever calculation depending on whatever the calculation is, and then it needs to write back the result. Right? So those of you who've taken computer architecture should be like pretty familiar. If you're not, don't worry, like this is what's happening. And I'll go over an example of hopefully makes this a bit more clear. So let's say you have 2 CPUs and there's a memory address of X that has 207 in it. And you have 2 CPUs. Both of these CPUs want to increment the X value by 1. So since you're incrementing it twice, you would expect the final value to be 209, right? So the first CPU increments it by 1. The second CPU also increments it by 1. So the final value should be 209 always, is what you'd expect. What actually happens when you break it down is, okay, the first CPU runs the first instruction, load X into R1. So CPU reads the memory, loads 207 into its register. it gets interrupted because so this is how multi-threading works, right? Like any point the CPU can decide to like the CPU or the OS can decide to reschedule the thread that's happening. It could happen at the same time. It could be a concurrent process in which the process decides to uh, stop execution of one thread and then start another, whatever reason. The second CPU also runs x equal to 207. And some of you can obviously start seeing the problem right here, right? So now say it gets interrupted again, and the second CPU does its add instruction locally. Right? So now 207 became 208 in the first CPU's register. It gets interrupted again. Now CPU 2 also thinks 207 was incremented once, it's 208. And then when you write it back, irrespective of what order they get written back into, X has been incremented twice, but it does not show in the result. Right? Does it make sense? Right? So what's happening here? Again, the problem here is we expect x equal to x plus 1 to be executed as one step by both the CPUs, right? But the problem is x equal to x plus 1 is not one step, it's multiple steps. And when you interleave those steps, this unintuitive behavior occurs, right? So this is what we mean when we say x equal to x plus 1 should be atomic. Okay. Any questions? Okay, cool. So how do you write atomics in C? This is what the next section is about. So instead of writing x equal to x plus 1, the language provides at least the GNU compiler and a bunch of compilers they give you a bunch of atomic functions, which if you use these, the compiler will guarantee that the code it spits out is atomic inside that. Like, so the first one is basically an atomic load, which says, don't worry about the syntax, you'll have time to parse this out. But the main thing to take away from this is using these functions in C, and different languages have different constructs. I think in Java, it's called atomic. They just use atomic. C++ has something called std::: atomic. You can use these also. So there are a bunch of different implementations to write atomic code. But the basic idea is that they're atomic, right? So the first one is an atomic load, which says if I read a value, then I read it in one step. The second one is an atomic store. If I'm writing it back, it should be atomic. The third one is an atomic add fetch, which says read the value at the address and increment it by 1 or whatever the value is, and store it back into that address in one step, which is what we saw in the previous example, right? So instead of x equal to x plus 1 cannot be interrupted if you use atomic add fetch. There's also an atomic fetch add. So what add fetch does is it adds the value and returns the result. Fetch add returns the old value and stores the updated value inside, right? It's just a ordering thing. The last two are basically it's sort of there are a class of operations called compare and swap. So what these are saying is that atomically put in the value into that address, but return the old value in one instruction without any interruption. The last one is sort of like an atomic load, but I think it's a bit faster because it expects Boolean or something like that. But it's basically saying whatever the value, put 0 in the address that I give. And again, all these are atomic instructions. There's a full list of atomic built-ins that you can use in GNU. We'll link those in the project notes. But this is what you need to write atomic code. And you need atomics if you want to synchronize. Otherwise, I don't think it's possible. And there might be some theory behind that. If you take a OS class or a computer architecture class, there are some principles like what are the bare minimum you need to write sane code in for multi-threaded applications. Okay, so makes sense. Okay, so if we look at the previous example, what do you think should change over here to make this work as we think it should? Any guesses? Yeah, exactly. Right. So you just replace the x equal to x plus 1 with atomic add. I'll get into what the last parameter atomic sequential consistency means. Don't worry about that now. If you don't get time to cover that, just use sequential consistency. But for now, don't worry about that. Okay. So makes sense so far, right? Okay. So is single field atomicity enough? Do you think it's enough, like to if is that all you need? Like, is that does it solve all your problems? Any guesses? I'll just go through it. It's fine. So this is some pseudocode. So it takes an object and takes in two values for two fields, and it sets the field 1 of the first object to F1 and the field 2 of object to F2. Each store individually is atomic, right? So if some object calls atomic store field 1 to F1, it will be set to F1. It won't get interrupted, right? There's no problem. So if I call, say I start two threads. The first thread sets mutate object to x comma x, set both the fields to x. The second one says set both of them to y, and they're running concurrently at the same time. Is there an execution possible in which field 1 is not equal to field 2? Do you get what I'm saying? Like, if thread 1 does mutate object, say thread 1 finishes first, then both the fields are x comma x. If thread 2 runs after that, it's y comma y. So depending on who finishes last, you would expect the values of the fields of that object to be of the thread that finished last, right? But would you expect it to be mixed up? Like the first field is x and the second field is y. Is it possible? It is. Who says no? Okay, so yeah, I mean, it is possible because even though each store itself is atomic, the atomics themselves might be interleaved, right? Yeah, so for me, I was mind blown when I saw this first time. I don't know about you guys if you've seen it or not, but yeah, this is something that to this day I still find it hard. Like when you actually sit and start writing these applications, it gets tricky. It can mess with what you're used to writing, right? So what can we do to fix this situation here?
Great question.
Oh yeah.
What causes this to happen? It seems like that's quite a long delay between the field 1 in X and field 2, that two instructions would.
Right. So the thing is, when you write application code, you don't really, at least for 99% of the cases, you're not in charge of the scheduling. So you don't get guarantees as to what the scheduling should be, right? So CPU can just decide to do it, or it depends on the OS scheduling, the CPU scheduling. There are a bunch of things going on. Basically, unless you explicitly say that I don't want this to happen, the execution environment can allow it to happen, right? So this is another point. So it's not guaranteed that this will always happen. So there are like some number of orderings. Few orderings provide the expected output. It could happen that there was no interruption and you get expected output. It could happen that this happens and this is not what you want. it could happen that maybe you're running on some hardware that does not do this. So it depends on the execution environment. So you need to know what exactly is going on. So it can happen. There are no guarantees to do that. Right? Any other questions? Cool. Okay. So what we, and those of you who've taken OS and have done some concurrency program, this should be pretty similar. So this should be pretty familiar. And what we say is this part, this red part over here is a critical section. You don't when a thread enters this section, you don't want any interrupts to happen and mess up the final write, right? You want, if a thread enters this section, you want that thread to be the only thread executing this part. And so what you basically want the thread to say, hey, am I the only one going to enter this part? And if it figures out that it is, it goes in there. And then any other thread that comes in sees that someone else is inside that critical section. So I should wait. I cannot go ahead. And then once the first thread says, okay, I'm done, and then the second thread is allowed to go through, right? So this critical section is called a critical section, and you guard access to critical sections via locks, right? Question.
Yes, so if you wrap that critical section around a block,
Mhm.
then do you actually need the atomics?
You probably don't. Probably you don't. But the locks themselves will be implemented with atomics. Right. Well, that's a good point. So if you're in a critical section, you don't need the atomics, right? You're not going to get interrupted inside, right? Again, this is correct only if no other code is accessing these fields at the same time. So you have to be careful about that too. Like some other code outside might be trying to read these.
Oh,
So then you might need it. So again, there are these tricky notions that you really have to think hard about. Yeah, and I'm still learning this. So you really need to like sort of be paranoid, at least is the sense I'm getting when you write multi-threaded code, right? Okay.
so let me just be clear.
Hmm.
So there could be that another function in another thread
Hmm.
could be accessing the object.
Right.
Object and so if I don't wrap it with an atomic, then although this part of the code is locked, but the object itself is not locked.
So we'll see an example where it's actually fine to do that. Like the code outside is, if it's just a read, it should be fine, but it depends on, again, where you're running it. Right. So yeah, I'm giving a hand wavy answer. I'm saying it basically depends. Mostly you don't need it, but you might need it. There might be cases where you need it. Like if this was not an atomic store, but if it was a atomic add, and then there was code outside which was reading that code, reading the atomic add, it might read something in between. Stuff like that could happen. Okay. Yeah, so it's not a definitive answer whether you need the atomic store or not. I'm saying it depends on what you're coding. Okay. But the important part is you have these locks that prevent access to this critical section.
You're not only the object there, right? Acquire object. So now you're only locking object. So which means you're only locking the access of other code to object, right?
Yes.
Then by definition, only one thread should be action. Other thread may start the action, just like object.
Yes. Yeah, okay. Yeah, you're right. So what we have here is only one thread is modifying this object in this function. You cannot have two threads calling this function and modifying the same object at the same time. Does that make sense? His question. So say thread 1 calls this function on object 1, acquires a lock on object 1's lock, is mutating object 1. If another thread comes and wants to modify object 2, it can go ahead because that lock is separate from the first object's lock, right? Does that make sense?
one can use object, right? Because object is already,
If they're two different, no one can use,
the object is already locked. No other program will use object.
sure, yeah, that's what I said.
You're saying other.
No, so his question was, if you're guarding this section with a lock, do you need the atomic stores inside? Because no other thread is modifying object, right? So you could probably get away with it. Again, I'm not going to commit to saying you don't need it or you need it, but I'm saying it would depend on what you're actually modifying. I'll just go over a quick example just to drill it in maybe one last thing. So say you have a database row. That row is guarded by a lock. So a thread comes in and it wants to do some work on that single row, right? There could be many rows, each row has its own lock. So the thread says, can I acquire the lock, right? And the lock says, go ahead, no one else is reading this lock, reading this row, so you can have the lock. And then the thread knows that the thread does its work with the assurance that nobody else is going to come and like interfere with it. And so if other threads come in and they're like, can we work on that row by asking for the lock? The lock says, hold on, like there's someone doing some work on this row. So I cannot give you the lock. You cannot process this row in a safe fashion until I tell you to. So this is what it means to acquire a lock, right? So thread one finishes its work, says, okay, I'm done. Take the lock back. I'm done with my work. And now the lock knows that the row is available for processing. So it decides which of these threads gets the lock. It cannot give it to all of them, because again, that would again be a problem. Make sure that one of them gets it, right? So this is the job of a lock, to make sure that only one thread is in some section of the code where you don't want multiple sections to be there, right? Question? Yeah,
Is not asking for the.
sure.
Trying to take some value from that row, give it a look still.
So this is again not a, so this is basically programming discipline, right? So say you're in a company and you have this database that you want to access. Someone new to the job comes and starts reading the database without acquiring a lock. There's nothing to stop that from happening. This is sort of like a protocol saying that if you're accessing it, this protocol could be built into the database itself, or it could be part of the middleware. But you have to make sure that everyone's following the protocol of acquiring a lock before modifying the row that you want to modify. So part of this comes to programming practices and discipline. Like, so there's a protocol. It's like implementing an algorithm wrong. Sure, if the algorithm is implemented wrong, then you cannot claim that's the algorithm's fault, right? So yeah, there's basically, yeah. Question? Yes. Yeah.
Not indents, if somebody is trying to read it, you can still read the loop, but not modify it.
Yeah, so that's a good question, and that's a segue into the next type of lock. So the lock here is basically a simple lock. It's an exclusive simple lock. Like the question that you're basically asking is, if a bunch of threads come in and all of the threads are saying, I only want to read this row, we should be fine letting all of them read the row, right? Because nobody's modifying the row. So even if you interleave, they all read the same value. So you don't need to lock out other threads if all the threads are only doing a read, right? But if again, if one of the threads wants to write, you need exclusivity again, right? So a reader writer lock, which is basically your project one, is an extension of the simple lock, which basically says, I'll allow concurrent reads, but only one thread is allowed to modify it at the same time. Does it make sense? Right? Any questions? Okay, again, same example, but with reader writer lock. So now that lock is a reader writer lock. The first thread comes in and says, I only want to read the lock. Okay, you get it. It only reads the row. It does not, it's again, this is sort of a promise that it won't write. Whether if it does write, it's a bug. Usually you can protect this, like the database could throw an error if this thread attempts to write it, right? So this is a reader thread, it's reading the thread. Bunch of other threads come in and they also say that I want to only read the row. It should be fine. Okay, you can have the lock, and all of them are reading the lock, right? Now, yeah, they're still reading the lock. They're still reading the row. A writer comes in, and the writer says, "Can I get the writer lock?" This time, the lock will have to say, "No, hold on. There are readers still working on that row, so I cannot give you the right lock, right?" And then the readers get done slowly. They release their lock, and now you can give the writer lock to it. So, quick question: when this writer is holding the lock, say two new threads come in. The first one is asking for a read lock. Second one's asking for a write lock. Can any of these threads get the lock? No, the write lock is an exclusive lock. You cannot allow them. So say now this is where it gets a bit trickier. So now let's say the writer is done, releases the lock, and there's a reader and a writer waiting for the lock. So when you acquire the lock, you're waiting for access to the lock. So say there's a reader and there's a writer. Who do you give the lock to? How many of you say reader? Oh, yes.
The one that came first.
Sure, that's one policy. Anyone has any other answer? Okay, so you're preferring write. So if there's a writer waiting, you always give it to the writer. The short answer is it depends on the policy that you want to implement, right? Few applications want to get writes done as quickly as possible, so you just give it to the write. If you're okay with who comes first, again, who comes first is sort of depends on the scheduling. But the question is, there is some leeway here that depends on the policy, right? There are lots of scheduling questions that come in once the lock has different behaviors for different threads. So say that the writer is waiting for an acquire write lock, and then there's a new reader that comes in and is also asking for the reader lock. So the first question is, is it okay to give the reader lock to the reader? Yes, right? Should you? That's a different question. Like that depends on your policy. So the problem with giving access to the reader while a writer is waiting is that your writers might get locked out. Your writers might never get the lock if there are a bunch of reads coming in. Does it make sense? Right? Yeah, this starvation, exactly. Starvation. Your writer can get starved out if does not get a chance to acquire the lock, right? So again, it depends on the policy. Maybe you're okay with it, maybe you're not. It depends on your application, right? Depending on how many reads and how many writes you're getting. Okay, so now the fun stuff starts. How do you actually implement a lock in C? Again, so this makes sense, right? This is the lock API. For a simple lock, you just have an acquire and a release. For a reader writer lock, you have two variants for each acquire. You have a read acquire, write acquire, read release, write release, right? Yep, I'll kind of spoil it. Project one is basically implement a read write lock. Okay, we'll give you code to show you how a simple lock works, and you'll have to implement a reader writer lock. Okay, so this section is something we can stare at for as long as possible. It took me a lot of time to understand this when I saw this. So we can spend a lot of time here. So these are two atomic functions that I showed you earlier. The first one is test and set, which says set the value to something and return the old value. And the second one is set it to 0, right? So say lock is the variable that controls whether the lock is acquired or not. So if lock equal to 0, that means the lock is free. Nobody has claimed the lock. If lock equal to 1, somebody has claimed the lock. We don't care who, but somebody has acquired the lock. Right? So given this knowledge, can anyone tell me what's happening in the acquired lock? Like take a guess. Like we can stare at this alone because understanding this is very critical to getting project 1 right. Right. So yeah, let's just stare at this for some time. If anyone who has not seen this before gets a sense of what's happening, just raise your hand. We can.
So, when locks, so this is a while loop, so.
Yes.
It tries to do the atomic. And when the log is 0,
Right.
it sets to 1
Right.
and returns 0.
Right.
And the while loop breaks.
Yes. Does that make sense to everybody? I'll explain it again. Basically, what's happening here is this while loop is sort of like a competition, right? So you have multiple threads. What this thread will only break if the old value was 0. If the old value was 0, and it'll always set it to 1. So every thread is attempting to set it to 1. But the one thread that changes it from 0 to 1 is the one who acquires the lock. Does that make sense? Yeah, we like mull over it a bit because this is really important. So the important thing is the thread which changes it from 0 to 1 is the thread that acquires the lock. Everyone is setting the lock to 1, but the thread which flips it to 1, flips the 0 to 1 is the thread that acquires the lock. Right? Make sense? Sort of, I mean, yeah, it's not very, it took me a lot of time to get this, but yeah, I mean, like, take your time. I mean, I'll leave this for 1 more minute. And the release lock is simple, right? Like release just, yeah. It's not. It's not. So this is kind of a bit of luck of the draw. Whatever the CPU or the OS decides its scheduling is, it's so we expect it to be fairly random. So it's kind of fair, but yeah, you're right. There's no policy implemented here.
So this is kind of like busy waiting. I mean,
Yeah.
all the threads are kind of active all the
Yes, yes. So there's no, yeah, you could be smart about this. You could say instead of trying to attack the lock every single time, I'm going to back off for some time and then try again. Like there's lots of policy things you can do over here. There's a policy that's like exponential back off. Like so one threads it tries the lock, doesn't get it, waits for 1 second. And then it tries for the lock again, waits for 2 seconds. Tries it still doesn't get the lock, wait for 4 seconds. So there are all these different policies that you can implement on top of this. But this is the core principle. Like this is the bare minimum you need to implement a lock. You need that atomic instruction. You need that atomic test and set. You cannot have the you remember the interleaving with the x equal to x plus 1. So if the first CPU reads a 0, sets it to 1, the second CPU also reads a 0 and sets it to 1. Now both the threads think they have the lock, which is wrong. So you need that atomic to ensure that only one of them gets to flip it to 1, right? So this is a simple spin lock. Yeah, so that's your project 1. Hold on. Okay, so I'll quickly show some stuff that should be helpful for. So I'm logging into. Okay. Yeah, I have a bunch of stuff I wanted to show in order, so I have the notes over there. But Yeah, oh wait, is the text? Is the text size okay? Or should I increase it? Sure. This is good. One more? Okay, okay. So, yeah, this is, I logged into the Kate machine, lab 110. There are instructions on how to log into the Kate machine. Just go ahead and, how many of you have never used SSIS before? Okay, command line. So Kate also provides a GUI. You can either go to the lab and actually work with the GUI and program in your. I don't think they let you install stuff, but if you have if you're more comfortable with a GUI, you can use that. They also have a remote uh, a remote GUI. Just go to the Kate lab and website and you can figure it out. For now, I'm just using the terminal. Okay, so on the right here is basically a process monitoring tool called Hipstop. It has one bar for each CPU core in this machine. And it basically tells you like how busy each CPU core is. These are a bunch of processes. Yeah, ignore the tough stuff at the top, it's just my notes. But so I will just show you one time. Yeah. Cool. Okay, so this is a simple benchmark that I've written. We have the log code. Yeah, sure. So maybe I can change it to, hold on. Does anyone know how to change the, wait. Does white look better? Appearance. Does anyone know where these, well, let me try this. Does anyone know a white color scheme? Oh, okay. Where are the lights? Lights. Which one? This one? This is by. Is it there? Okay, let me try this one more time. Yeah, we can try it one more time and then I'll give up. Settings, appearance. Yeah, colors. Okay, colors, color presets, light background. Okay, let me. Yeah, is this clearer? Much better? Sure, cool. Okay, yeah, I should have done this. Okay, so yeah, the first two functions are the lock implementation that we just saw, right? It's a simple spin lock, the release. I've written a work function that takes a pointer to a value, does a certain number of operations, like it tries to do some calculation some number of times, and it tries to acquire and release the lock some number of times, right? It's just doing some work, releasing the lock, and then trying to acquire the lock again, doing some work, right? So what I'm going to show is, so this is how you would normally compile C. Has anyone never worked with C before? So this is pretty clear, right? Okay. So yeah. So you try to compile it, it's going to complain saying that it doesn't have the threading library linked to it. So what you want to do is minus pthread, right? So the pthread says link this code with the threading code, right? It should compile now, right? And now I'm going to run the code. 16 threads, 100. 4, 5, right? Hopefully, if you should see the CPUs light up in the thing over there, right? So you can see like every core is trying to do some work. It's running. It takes some time. It took, I think this is in milliseconds. So this took around 8 seconds. There's just some simple benchmark that is. So the first thing that if you don't know is when I compile the code, I did not pass any optimization flags in. So the code the compiler spits out could be better, right? So if you want to optimize it, what you also pass in is this flag called -O3, or there are a bunch of flags you can also pass in OFAST. So if you pass in O3, it says apply the third level of optimization, like try to optimize the code as much as possible. There's another instruction which says try to generate code which is optimized for this CPU, right? So these are compiler flags, which if you don't know, this is something to know about. If you do, sure. Yeah. Okay, so I'm going to recompile the thing with these optimization flags. And I'm going to run the same thing again. It should be much faster, right? So the earlier thing took around 8 seconds. This took around like much quicker, right? So when you're compiling your project one code, we'll provide a makefile. And if you've never worked with, I can show you the makefile after this, but if you see all these funny symbols inside the makefile, this is what they mean. Okay, right? So now there's another tool that I wanted to show that will be useful for your project code. It's a tool called Perf, right? And what Perf does, basically the way it works is you run your process, and then what Perf tries to do is like it tries to interrupt the process and see where the process happened to stop at that point. So it does this a bunch of multiple times, like so it keeps sampling the location of where that code is executed at different points of time. And then, so if you do this enough number of times, you should get a good sense of where was your code taking the most amount of time, right? So this is a profiling technique called sampling. Question, right? So Perf is a tool that lets you profile your code. So I'll just give you a quick demo of how to run Perf on this application that we just compiled. So basically, if you want to generate a sample, what you do is you say perf record. So start collecting samples from the program that you're just running. And whatever you just ran before. I think this is what we ran. So it's going to run the same process, but perf is going to like poke in between some number of times and try to collect some data. So if you run perf, it's going to generate a file called perf.data, which is your sampled profiling picture. And if I want to check what the profile report actually looks like, I'm going to write perf report. Okay, so it says the program spent 98% of its time in this a.out work function, right? So you can like using the keyboard, you can just like hover over the section that you want to investigate a bit further, and you can hit enter, and you can say I don't know what zoom into means, but I'll just stick with annotate work. And it's a bunch of assembly code. If you can read assembly, sure, you can work with this, but it would be actually helpful to see the code that corresponds to this part of the assembly, right? You don't need to be an assembly expert. I'm not an assembly expert. You just need to know the basic like load, store, jump, compare, that sort of thing. But yeah, so you can see that this assembly section over here has no references to the code that you just wrote, right? So I'm going to quit. And so what actually happens is when you compile code with or without optimizations, I'm not sure what the compiler does is it strips out any references to the source code because it's not needed, right? If you do want those references, and this is useful if you're also using GDB, is to add a flag called -G, which says don't remove the symbols from, or keep the keep the keep the map of the assembly to the code that you've generated, right? So again, you don't need to type out these flags explicitly, but if you open the make file and these flags don't make sense, they should now, right? So I run the same thing with -G, right? And I regenerate the perf record. So it's going to do the same thing again. And I want to check the report again. So this time I go into work, I go into work, and now you can actually see the corresponding sections of assembly for the code that you just wrote, right? And now the interesting part that what I wanted to show was, so you can see, so the percent basically represents how much of the time this code spent on executing this line, right? And you can see here that 91% of the time was spent on this exchange assembly instruction. The exchange is a assembly instruction. I think it's specific to Intel. I'm not sure, but it's the assembly instruction which ensures that this test and set that you're doing is atomic. So if you have exchange over there, the spec guarantees that this will be atomic, right? So the point I'm trying to make here is that atomics are not for free, right? If you have multiple threads trying to update the same value, and you want those the most up-to-date value immediately, there might not really be a benefit to having it across multiple threads, because the threads have to synchronize anyway. Like they have to execute sequentially, right? Which is a subtle point in the reader-writer lock, right? So readers do not need the synchronization, but writers do. Hopefully this makes sense, right? So basically what I'm saying is atomics are not free. If you could, you'd want to reduce the number of times you use these atomics, right? So if you think about it, right? Let's say, which was the question like you were asking, is it okay to read a stale value, right? I'll show you. So say I did this. Is this still correct? Like, what do you guys think? So, okay, I'll explain what's going on here. So the first while loop is basically a competition, right? Whoever wins the competition exits. Like the rest of them are spinning on the while loop. Now we said atomics are costly, right? So what if instead of competing right away, I say, okay, I'll wait some time before competing. So I'll do a read which might not be the most up-to-date value of the lock, but I'm okay reading old values because the old value will be 1, right? So let's say the thread which acquired the lock released the lock. So now lock is 0, but all the threads are still reading the lock as 1, right? Which is fine, right? It still guarantees you that none of the threads are executing the critical section at the same time, but it might be it might acquire the lock a bit later. But the point is that's okay because you're not reading it via an atomic. Eventually, so remember when I said when the other thread releases the lock, the threads which are waiting on that lock might not see the most up-to-date value immediately, but eventually they will see that the lock was released, right? So you could do this. So this is, I'm getting into the little nitty-gritty details. If you don't get this part, it's okay. You don't need this part to implement Project One code. But I'm just trying to drive home the point that atomics are not free. Okay. So for now, just believe me that this works, even if you don't get it. And if anyone wants another explanation, I can try again. But you would expect this to work, but there's a bunch of subtleties that are going on that I wanted to show. So now I compile the code again, and I'm not going to run perf. I'm going to, you would expect it to go faster if things went as planned, but it's not going to finish, and I'll show you why. This is again just to drive home. Yes, yes.
Whichever ways, so it would still be in while loop itself. While
Yeah,
loop
but eventually the other thread should write it back to 0, and then it should break out of that inner while loop.
but it doesn't release it. It doesn't-
That's still release. That is still in the okay, I'll show this code. So the thread which acquires the lock gets out of this.
Also,
It-
it up the. It's also this and then releases the lock.
Right. So
What the other threads are doing.
the other threads are stuck over here. And until they see that the other thread has, so the other thread will atomically release the lock. The other threads might not see that immediately, but eventually they will see the new value. And when they see that it's 0, they'll break out of this lock and then compete over here again. That makes sense. So, but this is still deadlocking, right? Right. I mean, I just showed you that it's deadlocking. This is basically what's happening here is if so, I do perf record. I know it's not going to finish. So this is another thing about perf is you can cancel it in between, right? And I'm going to look at the report. I'm going to go into this. And yeah, so this is the new line of code that we wrote, right? If you notice this, right, those of you who know assembly, there's no comparison happening over here. This is basically saying jump to 29, okay, and it's basically stuck in this loop. So what happened to the variable lock over here? Okay, so basically what happened is the compiler thought that, hold on, when I'm inside this function, nobody is going to actually change the value of lock. So I can skip the comparison and just write a simple for loop. Like it thinks that the lock value is always going to be 1. So why do the comparison? I'll just spin there because it thinks it's this is basically an optimization gone wrong, right? So I'm saying that these things are, they get trickier the more you dive into them. So solution for this is basically, there is a keyword in C that you can mark a variable as volatile, and this basically gives a hint to the compiler that don't make any optimizations on this value here because someone else might change it, right? So please don't optimize this, right? So I mark it as volatile, and I compile it again, and then I run it, and it should be a bit faster, right? The earlier one took 1700 milliseconds. This one took 1100 seconds. This works as expected. And just for reference, let me get the perf record of this. And I do perf report. I go inside. And now you see the while lock, which earlier was just a simple jump instruction, and it was like stuck over there, is now actually, this is the while loop that you actually want, right? So this is just to show that once you start pushing for performance, things might not work as expected. So it's handy to know these tools so that you can like dig in and actually like work with the code and figure out what's going on, right? So if you don't get this part, it's fine. You can just stick to the normal sync. The stuff I covered in the lecture today, the atomic add and the syncs, the simple spin lock should be enough to implement your reader writer lock. But if you're interested in this kind of stuff, these are like things which can, at least I find them interesting, right? So, sure.
Please explain again why small piece of one if you optimize it.
because the compiler, uh, so if you don't have volatile, the compiler is kind of like pigeonholing into this function. Like the compiler is like thinking of, at least this is my understanding of it. It thinks that this is the only function, the only part of the code that I need to care about, right? So if so say I wrote this lock, right? Say I wrote this like this, while lock, right? And there was another piece of code which did this. Both are kind of the same, right? Right, like if you get stuck inside this loop, you will be stuck here. So you might as well just be stuck out. Like these two things do the same thing, right? So the compiler thinks that something like this is happening over here. And so it decides to basically change this to a while one. Like it thinks it's optimizing the code, right? But in reality, what it doesn't know is that lock could be changed by another thread. So then this assumption of these two being equal is not the same. The reason why this happens is like if you enter this while loop, right? Lock was 1, right? So now that you're here, lock is 1, because otherwise it would have not entered this section. So then now it thinks, okay, so lock, if I'm here, lock is 1 anyway. So why should I waste my time comparing it? I'm just going to say while 1. But what we need to tell the compiler is, hold on, that's not true. The value, and the other thing to note is that once we're here, nobody's writing to the value of lock inside this function, right? So the compiler thinks nobody's changing this value, and if I enter here, lock has to be 1. So why bother with the comparison operation? I'm just gonna make it a while 1, right? So to prevent that, we give the compiler a hint saying that this is a variable, a memory address that could be modified outside of the thread. So don't make optimizations to it. I mean, I think volatile is a pretty overloaded term. There are like other uses it's have, but in this context, this is what it is doing here. So once you mark it as volatile, the compiler cannot make this assumption anymore. So it does not optimize this part. Does that make sense?
Yeah.
Right? These things are tricky. There's actually another student in the lab, Hunter. He's an expert on this kind of stuff. So if I'm not able to help you in the TARs, we'll go bug him. Okay. So that is, I'm not going to save this. So everybody get some sense of the tools, perf, spin locks, atomics. We'll provide reading material in the project. So now I'll quickly show you the project. Yeah, ignore some of the files. So basically, you will be given this lock API, right? So this is the reader writer lock. We filled out the fields that we think you will need to implement the reader writer lock. Like, think about how to implement it. Like these two fields are enough to implement it. If you want to add more, go ahead. If you want to remove these, go ahead. But this is sort of like a hint. Like if you have these two fields, you can implement the reader writer lock. And over here, we have an API. There's the init lock, read lock, which is basically, the acquire read lock, release read lock, acquire write lock, release write lock, right? So this is the API that's given to you. And this is where you sort of need to like fill in the blanks and implement the reader writer lock, right? So you implement your reader writer lock, and we'll provide instructions in the README. I think there's also benchmark, which sort of similar to the lock bench that I showed you, which stress tests this code. It basically has a bunch of functions. So you don't need, don't modify this part of the code. This is the benchmark, right? This is what we'll use to test your implementation, right? So you implement the lock. Again, you have lots of time, don't worry about it. Usually this assignment, at least the last 2 times, was released the next week. But since the professor is traveling, we push this lecture ahead. So you have time. We'll probably release it tomorrow or Monday maybe, and then you'll have 2 or 3 weeks to do it. But hopefully everyone gets the idea, right? So you implement lock, and then let me quickly show the README. It's not up to date. I'm still working on it, but you should have. So you have your what you need to do in the lock, instructions to log into CADE, notes on like what a reader writer lock is. Yeah, so everyone knows what a makefile is. It's just a way to automate, instead of writing G++ that in the command line, you just write in a makefile and you wrap it around that. So these are instructions to run the benchmark and the arguments that the benchmark takes. And if you break the critical section correctness, that no reader and writer should be in the no 2 writers and or a reader and a writer in the critical section at the same time, it should panic and basically just stop, right? So if you get it correct, and this is another thing about multi-thread programs, it might run correctly once. That doesn't mean it's necessarily correct. So run it a bunch of times. You could get lucky, extremely lucky, and it could pass because it doesn't detect a race condition. I don't think that will happen, but if you set the number of like the workload very low, could happen. You'll get basically numbers saying that what was the performance of your reader and writer lock acquisition. And there's a bunch of like steps that I thought that I wrote that should help you with implementing this. So if I were to like do this, it was a different assignment when I took the course, but if I were to do this now, first thing I would do is making sure I get a correct version, which is like, don't care about performance, don't even care about multiple readers accessing the same part of the code. Just implement a simple read lock, exclusive lock. The only important thing is no 2 threads should be doing a thing which you think only 1 thread should be doing. So get that part right, and then start to think about how can you allow 2 readers to come at the same time, and then start working through those cases one by one. Use perf to figure out if you're stuck in a loop or something's happening. You could also use GDB, but I don't know how helpful GDB is for multi-threaded programming. So, but if I'll put some notes in to if you want to use GDB, right? And yeah, so perf is just to, again, yeah, I'm still working on this section. Perf is just to figure out what your code is actually doing and sample it, and you basically like submit a report, right? Is the clock stuck? Or? Okay, we have time. Any questions so far? A few other hints. The number of lines of code that you have to write is not too many, but getting them in the right order is important. So, yeah. Okay, and yeah, so feel free to ask for help in this project. TARs will post on the website Wednesday 12 to 2. If you can't make it, just drop me an email. We can work something out. Okay. Don't try to come last minute also. Things will get hectic. So you have time, but don't push it to the last minute also, right? It'll just be easier for all of us. It's not a very hard assignment, but try to yeah, start early, right? Since we have time, I covered this. I wanted, yeah, I'll let you go in like 5 minutes. I just briefly wanted to cover what that last parameter, atomic sequential consistency, means, right? So, so the second intuition that sort of breaks is so the first intuition that we saw was that do operations always happen in an atomic manner, right? And that could not or not be true depending on what you use. The second assumption is the list of sequences steps that you write in your program always execute in the same order, right? This is not necessarily true, because if you want to like squeeze out performance, the compiler can reorganize things. And CPUs these days, those of you, I think if you take computer architecture, this is covered in more detail, is that CPUs can do out of order execution. Like if it thinks two instructions that don't depend on each other, why do I have to wait for the first one to execute the second one? I'll just do both of them at the same time. This has consequences for when you do multi-threaded programming, right? So this is a really simple example. In these sort of tests are called litmus tests. Again, those of if you're really interested in this, I would encourage you to take Advanced Computer Architecture by Professor Vijay and Computer Architecture. They cover this in a lot of detail. But again, this is sort of the unintuitive behavior, as you can see with multi-thread programming. So say I have two variables, a equal to 0, b equal to 0. What thread 1 is doing is setting a equal to 1 and then printing b. And what thread 2 is doing is setting b to 1 and printing a. Can it happen that these two threads print like 0, 0? I mean, if you think instructions were happen in order, then if you print b first, then a has to be 1, right? So you cannot have the other thread print a equal to 1. Similarly, if you print a first, that means b was set to 1. So the first thread should print b as 1, right? You cannot see a case of a and b both being 0. That doesn't make sense, right? That means they were not executed in order, which is exactly what a CPU can do if it wants to. So basically, if you like remember the optimization we just saw, where the compiler decided, okay, we don't need this comparison, so let's skip it. What the CPU or the compiler might think is that the print b statement does not really depend on a equal to 1, right? So it should be fine if I'm the only thread executing to do the print first. Because print could basically be a read or a actual print, whatever it is. It's basically a read and a write. So it's reorganizing the read and a write inside a thread. It can do this. It wants to go as fast as possible. So it might, if you dive into the microarchitecture and all that, it makes sense to do this. But as a programmer, this again breaks your intuition, right? So so there's an entire field of study called like memory consistency models. It's basically what you want as a programmer is some assurance that some orderings are allowed or not allowed, right? So if you want one of the strongest assumptions is this like sequential consistency, which says that you do all your interleavings possible, but I don't want any output which does this read write overlap kind of thing, right? You do not want this to happen. So that's one memory consistency model. Again, I'm very I'm glossing over a lot of details, but what these memory consistency models define are the set of orderings that you're allowed to do. So if you say sequential consistency, this is not allowed, right? So there are other memory consistency models like release or relaxed. Relaxed basically says do whatever you want. Like I don't care if you reorder it. So you go as fast as possible. Acquire and release are sort of like if I write something, then everyone who executes after that should see that. You should not see a value before it. So there are all these reorderings that are possible. So I would encourage you to, like, if you're interested, to go and read about these memory reorderings. For this project, you can stick with sequential consistency. But if you finish fast and you think you can like improve performance with different semantics, like feel free to go ahead. Right? So that's what the last parameter in that atomic call does. It's basically saying, I don't want any fancy reorderings. Just do what I tell you, please. Make sense? Okay, I'm done. Yeah, any questions? We finished 15 minutes early. I'll stop the recording. Share.